Okay, so now that we know all the different symmetry elements, we can start to classify three-dimensional shapes, or particularly what we are interested in is molecules, into what are called point groups, okay? And point groups, as we said in an earlier video, are the complete set of all the symmetry elements, okay, that describe the overall symmetry of the molecule. And so all molecules fall into about one of 50 point groups. Technically speaking, there are infinite number of point groups, but it turns out that many of the point groups that do exist, there's no molecule that falls into that point group. So there's really only about 50 different point groups that we will be learning. And you know, there are patterns to all of these things, so it's not like you're just memorizing 50 different things. Point groups really range for how big they are, basically, you know, how many symmetry elements are in the point group. Some have very few operations, right? So a point group that is called C2V, for example. We'll go over that nomenclature in a little bit here, but that only has 4 symmetry elements. It has the identity, E. It has a 180-degree rotation, so that's a C2. And it has 2 different vertical mirror planes. So I'm calling one of those sigma V, and the second one of those sigma V prime. So that's an example of a point group, you know, not a lot of symmetry, only 4 elements. Contrast that with icosahedral point group, it's given IH. This has 120 different symmetry elements. Or some have actually infinite number of symmetry elements, and we'll explain that in a bit, but that would be an example of those is like a linear molecule, C infinity V. And so once we dive into a particular point group, we talk about elements that are similar, okay? And elements that are similar are called a class. We group them into a class. They're mathematically similar, and they also just feel similar, okay? So for example, E it's in its own class. E and then version are always in their class by themselves, okay? You only can have one E, one identity, and you only can have one inversion. And those are always by themselves. They're special that way. In this point group for C2V, C2 is in its own class, but these 2 sigma V's are similar, right? And so you might think that those could be in the same class, and that's the proper way of thinking. We will give a more mathematical definition later on in the course about how to determine if 2 symmetry elements are in the same class, and that is an important skill. But for now, we don't have to worry about it, and we're just going to kind of use our intuition, ones that feel similar, okay? So when we're talking about different types of point groups, we can kind of break them up into different categories. First, there's the linear molecules, linear point groups. These are things like carbon monoxide, diatomic oxygen. Oftentimes, these only have 2 atoms, and then they're going to be linear. That's all you can do with 2 points, right? But they could have 3 atoms. For example, carbon dioxide. You know that if you remember the Lewis structure, carbon dioxide, that has 2 double bonds. And so that's actually a linear molecule. So that would be a linear point group. There's also those that have very high symmetry. So we're talking about tetrahedral, like methane, octahedral, like sulfur hexafluoride, icosahedral. There's certain boron complexes that are icosahedral, but these have really high symmetry. Then there's the C groups and the D groups, and those with very low symmetry. So the C groups have a CN, a rotation axis, without any perpendicular C2s. The D groups have that same CN, or have a CN, they at least have one CN, but more than one CN, they also have N perpendicular C2s. And it turns out all you need to know is you just need to find one perpendicular C2 to the principal rotation, CN, and that tells you you're in a D group. And then there's also the last category is the very low symmetry. So these molecules maybe only have the identity, we talked about those earlier, or just have a mirror plane or just have an inverse. They're pretty rare, but they do exist. And so what you're going to do is you're going to use a flow chart to figure out how to name these 50 or so more point groups. So you're going to get a molecule. The beginning of 90% of the questions in this course are going to start this way. You're going to get a molecule, draw the structure, or you're given the structure. Based on that, what is the point group? And that might be the end of the problem early on. Later on in the course, we're going to do a lot more other stuff about spectroscopy, etc. But it's going to start this way. So you're going to use this flow chart and go through. So let's just say I have a molecule. And so the first thing I'm going to do is ask myself, is it in a special group? Okay. What does a special group mean? It's either linear or a very high symmetry group. Okay, that's what I'm calling on this flow chart. What is a special group? So if it's a special group, you're going to go down this way. Okay. If it's not a special group, you're going to go up here. So let's say it's not one of these special groups that has sort of intermediate symmetry. Then you're going to ask the question, is there C2 perpendicular to a principal rotation axis? And you can see if you say yes, that takes you down this funnel where you go into the D groups. If you say no, that's all the C groups or the S groups. S groups only have improper rotation axes, okay? You can see, so let's say no, and then we say, is there a mirror plane? Yes, if there's a mirror plane, then we go down here. Is there a mirror plane perpendicular to the CN? Let's say no, that would be a CNV. So if you had a CN, your principal rotation axis was 3, a C3, you'd be C3V. And so in this way, that's how you go down. Let me just, there's some other sort of not very common ones here. So let's go over that. I mentioned SN. That means it just has identity and the improper rotation axes. Those are very rare. C1, these are low symmetry ones now. We're in very high symmetry. No. C1, that means it just has identity. CS, that means it just has a mirror plane. And CI means it just has inversion. These ones are different icosahedral, octahedral, and tetrahedral ones. If it has no subscript, it doesn't have any mirror planes. If it has an H, that means it has a horizontal mirror plane. And if it has a D, it has a dihedral mirror plane. Okay. And then there's C infinity V and D infinity H. And so those are linear molecules that also follow this C2. Is there a C2 perpendicular to the CN? So if there is, it's D infinity H. And the nomenclature of H there tells you there's also a horizontal mirror plane there. We'll go through these and it will get easier. The last thing, I want to tell you is that there's a lot of different flowcharts out there. You can find a lot online. I post one that I like. I posted it on our web campus website, but it doesn't matter which one you use. There's several ways to get to the same answer. Just make sure if you're using a different flowchart, you are consistently getting the same